Today we'll be looking at metal foams. This is an introduction into what they are, how they're made, how they're used, their pros and cons, and what their future looks like. So what are metal foams? A metal foam is a porous metallic structure. They are often, much like other foams, either open or closed cell. This image here shows an open cell structure where none of the individual cells are completely closed off, so a fluid such as water or air can pass through them. Open cell foams will be the primary discussion in this presentation. Common materials of metallic foams include aluminum and titanium. However, lead, magnesium, gold, zinc, copper, bronze, and steel are all material types that Michael Ashby, in his book Metal Foams, a Design Guide, outlines. ERG Aerospace, which is the manufacturer of Duocell foam, also lists tin, Inconel, and nickel as metallic foams that they manufacture under the name Duocell. And also silicon carbide, ceramics, and carbon are similar materials. However, they are not technically metal and will therefore not be discussed in this presentation. Okay, so how is metal foam made? Ashby lists 9 ways of metallic foam production, 5 of which being established commercially. Of these, there are 3 broad classes of manufacture techniques. These include vapor phase formation. Often this is some form of a vapor deposition, often depositing onto a foam substrate that is then later burned or melted out to leave behind the metallic foam structure. Liquid state processing is a very common technique outlined here in this photo from Ashby's book. In this case, a gas is blown into a liquid form of the metal, and then essentially the bubbles are captured as the metal foam. Lastly, there's some solid state forming techniques. Often a metallic powder is sintered into either the metallic foam shape or sintered with a trapped gas under high pressure that is then expanded during sintering to create sort of a blown up metallic structure. These processes all vary with the type of material, with some processes being ideal for certain materials and not for others. So what your end product material is specifies your, or at least limits your processes. Okay, so how are metal foams used? There are several applications that ERG Aerospace lists on their website, and have some examples. Here is an air oil separator from a Honda Jet, actually. An air oil separator separates hot engine gases from the oil inside of them, so the oil can be drained back into the engine and reused. They also talk about heat exchangers. All of these applications, the high surface area of the metallic foam proves them ideal for. This heat exchanger was used on the ExoMars lander, and again, a fluid or air being pumped through here will exchange a lot of heat due to the high surface area. Other applications include baffles, flame arresters, energy absorbers, breather plugs, and CO2 scrubbers. Here's an example of a baffle. A baffle like this provides resistance to a liquid sloshing around. So this might be inside of a tank. So when the tank is only partly full, the liquid is limited in how easily it can slosh back and forth, yet the structure is porous enough that it can still drain through and be used. Flame arresters with a similar structure will simply slow the spread of flames through a structure or a part. Kinetic energy absorbers, or simply called energy absorbers, will slow airflow through them or fluid flow through them, and that reduction in speed will capture its kinetic energy. Breather plugs are essentially a filter much like this baffle that's used on the vent of a fluid container to keep fluid that sloshes from sloshing out. It'll sort of capture that and like a filter and let it drain back in. CO2 scrubbers, they were used or are used actually in the International Space Station. They require both a heat exchanger and a form of a trap for its media. Uses some chemical pellets to help scrub CO2 out. And the porous structure of a metallic foam both holds that media as well as transfers heat well and provides an ideal application for metallic foams. Also, there's acoustical applications of metallic foams, like this microphone demonstrated here, where the foam will break up wind noise and help create cleaner audio recordings, much like a conventional foam over a microphone, except these are going to be a little tougher and withstand harsher environments better. ERG also produces electromagnetic interference shields, like this one pictured here for a Pratt & Whitney turbofan engine that would be used on an airliner, for example. The internally reflective nature to electromagnetic radiation of this foam means that while it is very light and fairly rigid as this box here, it is relatively sealed in the sense of electromagnetic radiation getting either in or out. So you could house really sensitive electronics inside of here, or electronics that produce a lot of electromagnetic radiation, and the box would trap it and keep it from interfering with other nearby systems. Lastly, there's a bunch of mechanical applications of metal foam. It is relatively stiff and thermally stable, which proves ideal for things like this mirror here in like telescopes and satellites, where a stiff, lightweight structure is required to keep a mirror flat and in position. And also the metallic foam is thermally stable in that it doesn't expand and contract a whole lot with temperature changes. All of these are factors that could deteriorate the performance of a mirror if it does not remain perfectly flat and dimensionally accurate. So next up, we look at the advantages of metal foams. Some advantages include that they are very rigid and have a high strength to weight ratio. This provides good mechanical properties for things that require rigidity. Their density can be varied based on the pore size. This can be ideal for filtering various types of media, various sizes, trying to trap only a certain particulate, for example, or in cases of flotation or things that need specific weight, the overall dimensions can remain the same, while changing the density can affect its both mechanical and filtration or buoyancy or otherwise related properties. Another advantage is that metallic foams are conventionally machinable in that they behave similarly to the material which they are made out of, often aluminum. So any machine that can machine and change the dimension of a solid aluminum part can similarly machine a aluminum foam, and that provides a ease of tooling in that conventional tools that most places are already going to have can be used with metallic foams. The other great advantage of metallic foams is their thermal stability, in that they remain fairly stable in their dimensions as temperature changes. All of these are advantages listed on Duofoam, ERG Aerospace's website, and are obviously going to be listed by them, being that they're a manufacturer trying to sell their product. Some drawbacks of the metallic foam are their poor definition and size constraints due to their pore size. If you look at the structure here on the right, you can see it's a fairly open, loose structure, and depending on what density and pore size the material is, fine details don't hold up well. Sharp edges, specific contours, sharp angles, anything like that don't hold up well simply because there's not enough material to hold small dimensions. If you start getting on the scale of the individual cells, you get very jagged edges. So very detailed parts are not well suited for metallic foams. This is actually listed on ERG Aerospace's website as one of their drawbacks. And for some other drawbacks, we can look at Michael Ashby's book, and the entire lengthy section on how to do strength calculations for bending and shear and torsion, etc., indicates that there's some pretty complicated math there, as well as the individual factors being potentially hard to determine and very dependent on exactly how the structure of the foam is, which cannot necessarily be precisely controlled in manufacturing processes. Other observations I personally have made includes the high surface area makes the material susceptible to corrosion, also simply because it can easily trap liquids, and therefore is susceptible to corrosion. ERG does offer plating onto their foam. For example, you can get a gold plated foam, which will then be fairly stable and resist corrosion. However, that's going to add cost as well. The other issues I see with metallic foams is that the individual shapes and potentially sharp corners left internally from the manufacturing process means the foams may be susceptible to cracking over time, especially subject to vibration. And lastly, being that their structure is not continuous in a sense, they're going to be difficult to inspect, especially for things like cracking. Being that there's so much surface area to inspect and so little of it that's actually accessible to inspect. So lastly, we look at the future of metallic foams, and we see it's a rapidly developing technology. It has massively increased in recent years and is likely to continue to develop. I foresee it becoming more widely used as the manufacturing processes take off and provide more stability and more consistency in the material and more variability in design characteristics, what can be done with it. It's a very promising material to be used in a lot of applications, as previously listed. I foresee use in composite panels where two solid material, for example, aluminum panels, are spaced off with a metallic foam between it to provide rigidity, much in the way we use honeycomb panels in composite structures today. And surely advancements in the manufacturing of the foam will lead to more utilization as some of the drawbacks are overcome and controlled. Here's just the works referenced here: Metal Foams, a Design Guide by Michael Ashby, and ERG Aerospace's website. They're the manufacturer of Duracell and provided most of the photos in this presentation. Thank you.